True or false? When an object is solely under the influence of conservative forces, the sum of its kinetic and potential energies does not change. So that's definitely true. That's sort of the definition for conservative forces, is that K initial plus PE initial equals KE final plus PE final. Using the data from table from your book, shown below, estimate the energy needs of a person over a 4-hour period if they do the following activities. So sleep for 1 hour. The energy is going to equal 3,600 seconds times 83 watts. Walk a distance of 5 kilometers to school at a constant speed of 5 kilometers per hour. So remember, V is equal to D over T. So T is equal to D over V. 5 kilometers divided by 5 kilometers per hour equals 1 hour. It takes them 1 hour, so that's 3,600 seconds. So this energy is equal to 3,600 times walking, 280. I'm also going to use that 1 kilocalorie equals 4,184 joules. So I'm going to divide by 4,184. Sits in a class for 1 hour. So I've got energy here is equal to 3,600 times sitting in class, 210, divided by 4,184. Standing relaxed, talking to a friend for 40 minutes. So 40 minutes is going to be 40 times 60 times standing relaxed, 125, divided by 4,184. And cycling on a bike share distance of 5 kilometers. So again, T is equal to 5 kilometers divided by 15 is equal to 0.33 hours. So it's actually equal to, it's going to be 20 minutes on the bike. So it's going to be, E is going to be 20 times 60 times cycling is 400 divided by 4,184. So now let's just figure these all out. 3,600 times 83 divided by 4,184 is 71.4. 3,600 times 280 divided by 4,184, 241. 3,600 times 210 divided by 4,184, 181. 40 minutes times 60 seconds times 125 divided by 4,184 is 71.7 calories. And the cycling is 20 minutes times 60 seconds times 400 divided by 4,184, 114.7. Lastly, add up all the calories. 71.4 plus 241 plus 181 plus 71.7 plus 114.7 is 679.8 kcals. C. You push a box initially at rest across a horizontal floor. There is a constant kinetic friction force on the box Fk while the box is sliding. If you do W of work on the box as you push the box forward a distance d, what will be the final kinetic energy of the box? So you're pushing with some force times d is going to be plus the work that you do, right? So the E initial plus the work done by all the non-conservative forces equals the E final. Energy is kinetic plus potential plus the work that you do minus Fkd. That's the work done by friction. Friction does negative work on the box as it travels, is equal to Ke final plus Pe final. Also, it's a horizontal floor, so Pe initial equals Pe final. So you can subtract that from both sides. Also, it's initially at rest, so kinetic energy initial equals 0. So just rearranging this, you get the kinetic energy final equals the work you do minus this Fk times d. Question 6. A sports car accelerates from rest along a straight, flat, horizontal track. V initial equals 0. You may assume that the power of the engine accelerating the car is constant. Work divided by delta T is constant. The efficiency is constant. Air resistance is negligible. It takes a time T1 to get to 0 from 0 speed to a speed of v1. So the power here, I'm going to say, is the change in kinetic energy of the car divided by that change in time. So it's going to be 1/2 m times v1 squared divided by t1. It says, how long does it take to get from 0 speed to 2v1? So I would say that same power is equal to 1/2 mv2 squared over t2, and that's 2v1. So it's 1/2 m times 2v1 squared over t2. It's the same power, so I would say that 1/2 mv1 squared over t1 equals 1/2 m times 2v1 squared over t2. The half m's cancel. v1 squared over t1 is equal to 4 v1 squared over t2. The v1 divided both sides by v1 squared. You get 1 over t1 equals 4 over t2. Cross multiply, you get t2 is equal to 4 times t1. An energy-efficient refrigerator uses 150 watts of power when it is operating due to good insulation. So the good here is power is equal to 150 watts. The time that it's operating or something is equal to 0.2 times t total or whatever of the day. And the bad refrigerator has a power of 350 watts, and its operating, t operating, is equal to 0.25 times t total. And in each case, the rate here that we're paying is equal to $0.13 per kilowatt hour. So we can immediately convert this to kilowatts. 0.15 kilowatts. The bad one has 0.35 kilowatts. How much money do you save over 30 days? So T total equals 30 days times 24 hours. T total is 30 times 24, 720 hours. So the good cost is going to be 0.15 kilowatts times 720 hours times 0.2, because it's only operating 20% of the time, times the rate, $0.13 per kilowatt hour. So the kilowatts cancels the kilowatts, hours cancels the hour, and you get 0.15 times 720 times 0.2 times 0.13. It's going to cost you $2.81. And the bad cost is 0.35 kilowatts times 720 hours, times 0.25, because it operates 25% of the time, I guess worse insulation, times the same cost, or same rate, 0.13, 0.35 times 720 times 0.25 times 0.13, $8.19. So by getting a good refrigerator, you're saving $8.19 minus $2.81, saving $5.38, which I think was the answer C. This letter, shown in the figure below, starts from the top of a frictionless hill and slides down into the valley. What initial speed VI does this letter need to just make it over the next hill? So I'm going to call this V final equals 0 here. And so it's pretty straightforward. You've got E initial equals E final. There's no external work being done or something like that. So we write that out. 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus m times g times h final. And so, yeah, I guess there's m's in all the equation. All the terms here, cross out m's. And we're also going to say v final is equal to 0. So we've got v initial squared over 2 plus G times H initial equals G times H final. So V initial squared is equal to 2 times G, I guess, times H final minus H initial. So V initial is equal to the square root of 2G times H final minus H initial. So square root of 2 times 9.8 times 42 minus 30. 2 times 9.8 times, I think 42 minus 30 is 12. Take the square root of that thing. 15.33 meters per second, closest to B. A hiker of mass 78 kilograms takes 1.5 hours to climb a mountain. So there's the mountain. There we are. M is equal to 78. During the climb, the climber's vertical elevation increases by 360 meters. Okay, what was the power of the process needed to increase the gravitational energy? So the gravitational energy here is, I guess, going to be delta that is going to be m times g times h, and then the power is going to be the change in potential energy divided by the change in time. And let's not forget, these are all in watts, I think. The W stands for watts. So we're going to need to convert this 1.5 hours into seconds. So delta T is equal to 1.5 hours. I'll multiply that times some number of minutes per, minutes per hour. So I know that there's 60 minutes per 1 hour, and then I'm going to multiply times seconds per minute. I know there's 60 seconds in 1 minute. This way, minutes cancels with minutes, hours cancels with hours, and we get 1.5 hours times 60 minutes per hour times 60 seconds per minute, 5,400 seconds. So this is going to be equal to 78 times 9.8 times 360 divided by 5,400. 78 times 9.8 times 360 divided by 5400, 50.96. And that is going to be in watts, closest to 51 watts.